This is unit number 6, video number 6, the heating curve. We'll look at now combining the phase change with the heat capacity. We've seen specific heat capacity is the heat to change temperature in a phase, and then we've seen heat of fusion, heat of vaporization, heat of sublimation is the energy to change across a phase. So now we're going to look at what does it look like if I just take a substance as a solid and heat it until it's a vapor. Okay. Well, I've got here a little graph, and on our x-axis we have the heat added. This is going to be in kilojoules, so we're adding heat. On the y-axis we have our temperature, okay, in degrees Celsius. And I've got marked clearly the boiling point and melting point of water. So this is going to be a heating curve of water. Not necessarily to scale, I'm not going to use an exact number, so I'm just going to show you the general form. So if I have some ice, and I begin to heat it, it's going to change temperature. Ice can be colder than 0 degrees Celsius. We know that. It can be enormously cold. So we start it at some lower temperature, maybe negative 25 degrees Celsius, and we begin to add heat to it. It will increase temperature until it reaches 0 degrees Celsius. At that point, it stops increasing temperature and begins to convert phase. We're still adding heat, but that heat is now changing the phase, not the temperature. So it's going to flatline. So we'll get a flat line there as all of the ice is melted. So here I have solid water, and here I have liquid water. Both exist at 0 degrees Celsius. Okay? Once I have completely converted my solid into liquid, then I'm going to begin to heat up. And I'm going to go across like this. That should be a straight line. Not very good. It's going to be a steady slope. The slope is the specific heat. So we've got a steady slope here, and we're going to raise temperature of the water as we're adding heat. The temperature is going up until we reach 100 degrees Celsius. Then it's going to stop again. We're going to continue adding heat, but that heat is no longer going to raise the temperature of the water. It's going to boil it. So now we're vaporizing it. So we're going to get a vaporization line until all of it is vaporized. Here we have liquid water at 100 degrees Celsius. Here we have vapor or steam at 100 degrees Celsius. Once the steam is completely converted, all the liquid has been converted into the gas, then we can begin to heat the steam. And we'll get that kind of thing there. So the heating curve is going to show us these steps. Now, what's governing each step? Well, this is heat capacity. Q equals SM delta T. But we're probably going to do this in moles. So if we do it in moles, we usually write the S as a C for heat capacity times the number of moles times temperature change. That's also going to be the formula for this line and the formula for this line. So each of our diagonal lines are governed by heat capacity. We can do it in mass, or we can do it in moles. What about our phase changes? Well, now we have Q equals the heat of fusion times the number of moles. That's going to govern how long this line is. Okay? So that flat line is the Q equals the heat of fusion times the number of moles. Up here, Q equals the heat of vaporization times the number of moles. So heat capacity governs the change of temperature inside the phase. There's a different heat capacity for the solid versus the liquid, meaning liquid water takes twice as much heat to change temperature as ice does. And same thing with steam. Both of those are about half of liquid water. Okay? And then our flat lines are governed by our heat of fusion and heat vaporization.